Hello, I am Subhasri Chatterjee. I work with Professor Panikos Kyriakou at the Research Centre for Biomedical Engineering at City University of London. My postdoctoral research project is supported by the industrial partners Rockley Photonics and Samsung Advanced Institute of Technology. Um, our main aim is to design a wearable sensor based on PPG technology. The part of this work is to investigate the influence of the vessel depth on the light tissue interactions in reflectance photoplethysmography, which I'm going to talk about today. Photoplethysmography, in short PPG, is an optical technique to measure the volume changes in blood. The most popular use of PPG can be found in pulse oximetry, which is the technique to measure the arterial blood oxygen saturation in the clinical setting. Um, So experimentally, when a PPG signal is acquired, typically a sensor is placed on the peripheral tissue site, such as finger or forehead or forearm, etc. Um, so in the sensor, there is an optical source which illuminates the tissue with the light intensity, and the scattered light from the tissue is recorded by the detector. Now, through the cardiac cycle, there is a change in the blood volume within the tissue. During systole, blood rushes to the periphery of the tissue of the human body, resulting in a higher blood volume in the peripheral tissue site. Higher blood volume results in higher absorbance of light in that tissue area. Again, during diastole, the blood volume in the peripheral tissue site decreases, resulting in a lower absorbance. So, from systole to diastole, clearly there is a gradual change in the optical absorbance, which continues throughout the cardiac cycle. So, this continuous change of the optical absorbance basically results in the PPG signal. This is shown in the schematic given in the figure B, and figure A is basically a typical PPG signal which was recorded from a healthy volunteer in our lab. Now, in recent past, there have been a lot of studies which are focused on the improvement of PPG technology, acquiring signals from very complicated places to have higher signal quality, to reduce the motion artifact, to improve the signal to noise ratio, etc. But the fundamental aspects of PPG has not been very well investigated. Among several fundamental questions, one of the remaining question is how a large artery or large blood vessel affects the PPG signal. Some of the studies are available which actually show that placing a PPG sensor directly on a large artery actually gives very erroneous results. So, but there have not been any study dedicated to the understanding how basically the large vessel or its depth from the tissue top surface of the tissue volume affects the PPG signal or the working principle of a PPG sensor. These kind of studies are very important for any wearable sensor design. For example, if we design a wristband sensor, then how the underlying radial artery will affect the PPT signal is very important to understand for specifications of the sensor. So the current work basically investigates this aspect, and we use a Monte Carlo model for this work. I have chosen Monte Carlo method for my work because this is a stochastic method which gives reliable outcomes. Monte Carlo method is a very well-known computational approach for solving biomedical optics applications. Monte Carlo model gives us flexible input and output variables. It can incorporate any kind of heterogeneity of the tissue layer and scattering anisotropy. It has no limitation regarding the geometry. So these are the main reasons why Monte Carlo method is the most suitable choice for this kind of study. In this work, we have considered a simple tissue model which was designed having a slab of fat tissue with an embedded blood vessel in a reflectance PPG geometry. So as you can see in figure A, the schematic of the tissue geometry for the Monte Carlo simulation, which is represented in a 3D Cartesian coordinate system XYZ. The optical source is supposed to be placed on the origin of the coordinate system, and the detector is placed at a certain distance from the source, both on the tissue surface, that is along the x-axis. Z-axis here represents the depth within the tissue, and y-axis represents the width within the tissue. Here we have considered the radius of the blood vessel to be 1.5 millimeter, and the depth of the axis of the blood vessel was varied from 2 to 10 millimeters in this model. Figure B represents the flowchart for the Monte Carlo simulation. So I will very briefly cover the steps I have used for this simulation approach. First, a new virtual photon packet is launched onto the tissue surface. Then, after the correction of the boundary reflectance between the air and the tissue, a new step size of the photon is calculated. This is calculated by the random sampling of the free path length probability of the photon within the tissue. And then the photon is moved through the step size. Now, after each step size, it is checked if the photon has hit the boundary. In this model, we don't have we have a semi-infinite model, so we don't have a restriction in the bottom tissue layer. Each time we check if the photon has transmitted to the upper surface of the tissue volume. If the photon is transmitted, then it is checked if the photon is detected. That is, if it falls within the detection criteria. In this case, which is it's come within the area of the detector. Then the photon variables such as reflectance, transmittance, optical path, depth of penetration, etc. are recorded. On the other hand, if the photon does not hit the boundary, that means it remains within the tissue. Then the scattering and absorption are simulated. So scattering angles are calculated based on the Heinrich-Greenstein phase function. And after all these calculations, the photon variables such as photon weight, photon path length, direction, etc. are updated. Then it is checked if the photon survives. So if the photon weight falls below a certain threshold weight, in this case which is 0.0001, then the photon is considered terminated. Now, for conservation of energy principle, we use the Russian roulette technique, where 1 in 10 photons get an opportunity for surviving with an additional weight. After this step, we always calculate if this is the last simulated photons, or if not, then all these steps are repeated until a desired number of photons is recorded. Some other considerations for this model. So as I said already, a simple model of slab layered tissue with a blood vessel considered in this work. The blood vessel was considered as a cylinder filled with oxygenated blood. So in this work, we have not considered the vessel wall properties. In this model, we have considered the refractive index of the entire tissue volume to be 1.4, and of course the air refractive index is 1. The refractive index mismatch between the blood and fat tissue layer has not been considered in this model. The model has been executed at 660 nanometer and 940 nanometer wavelengths. So these two wavelengths were chosen for this study because these are most commonly used wavelengths at pulse oximetry, and also the primary choice for any PPG based technology. We have carried out the simulations throughout a range of source data separation of 1 to 12 millimeter. In table 1, you can see the optical properties used in this model. Absorption coefficient, scattering coefficient, and anisotropy factor of fat and oxyhemoglobin tissue at 666 940 nanometers wavelengths have been presented here. Let us go to the results now. So these figures show the distribution of photon scattering. So In Monte Carlo model, we actually simulate the three-dimensional distribution of the photon scattering events. Here, in the first row, we represent the exact plane projection of the model, and in the second row, we present the YZ plane projection. Color bar represents the number of scattering, which is distributed between this minimum and maximum values in min and in max. Along the Z direction, the penetration depth within the tissue is represented. In the first row, the x-axis represent the width of the tissue, and in the second row, it represents the thickness of the tissue. Now, you can see that the maximum number of photons are accumulated within the first few millimeters of the tissue layer from the top surface, and gradually the number of photon or number of the scattering events decreases. Now, this this concentration of photons are basically within the blood vessel, which you can see gradually decreases, gradually goes deeper within the tissue because of the given criteria, that is the vessel depths are 2 millimeter, 4 millimeter, 6 millimeter, 8 millimeter, and 10 millimeter. You can see the roundish shape of the vessel in this YZ plane view, and it is very clearly seen that the photons are basically accumulated in the fat tissue layer and in the um, within the blood vessel. This slide represents the recorded variables for different geometrical and anatomical settings. So here, by geometrical setting, we mean to different source director separations, which is from 1 to 12 millimeters, and the different anatomical settings represent different vessel depths within the tissue, which is 2 to 10 millimeters. So the first row represents the result for 660 nanometer wavelength, and the second row represents the result for 940 nanometers wavelength. Mean optical path, which is presented in the first column of this figure, shows sharp increase of the optical path length for both wavelengths throughout the range of source director separation. Now, this is the optical path length throughout the entire within the entire tissue volume. The second column represents the optical path length only through the blood vessel. So we have studied both these separately to understand how light propagates through the tissue and through the blood vessel. So we can see different behavior of optical path length in these two cases. So unlike this total optical path length, the path length through the vessel initially increases with the source director separation, and then it becomes almost steady for the higher source director separation. Also, for a different vessel depth, the total optical path length are almost the similar for 660 nanometer, and the change at 940 nanometer is also not very high. But through the blood vessel, for the different depths of the vessels, you can see the difference between the optical path length are quite high. This third column represents the penetration depth throughout the source director separation. So for 660 nanometer, we can see that the penetration depth initially increases and then it becomes sort of plateaued, whereas for 940 nanometer, it sharply increases with the increasing source director separation. And finally, the fourth column represents the reflectance. So reflectance is basically equivalent to the experimental PPG intensity. So you can see that the reflectance decreases with the increasing source director separation at both the wavelengths. Total reflectance at 660 nanometer is much higher than total reflectance at 940 nanometer. This is because the absorbance at both fat and blood is much higher at 940 nanometer compared to 660 nanometer. So to conclude, Um, we represent here a simple model of biological tissue volume with an embedded blood vessel that is representing a reflectance PPG geometry. The effect of different vessel depth on the light tissue interactions are presented in this work. We have found that the total optical path length increases steadily with increasing source data separation at both wavelengths, whereas the path length through the vessel becomes constant at the higher separation. We also have found that the depth of penetration increases and reflectance decreases with the increasing source data separation. Future plan from this work includes the simulation with complex models having multiple tissue layers and both artery and vein, and to investigate the sensor feasibility across and along the vessels. The in silico investigation will be accompanied by the in vitro experiment with a tissue phantom having blood vessels at different depths and a Windkessel model representing a PPG system. The information obtained from such studies are invaluable for the wearable PPG sensor design, for example, a wristband sensor for physiology monitoring, which is our ultimate goal. Here I have given some references which are related to this investigation. So the first one is the multi-wavelength PPG model, which we already published. However, it does not consider a large vessel because it is on the finger tissue model. It has a very complex uh, finger tissue model and a very detailed analysis on that. The second reference is for the in vitro investigation, and the Windkessel model will be using for our further experimentation. The next reference is obviously by Stephen Jacobs and his team, and which gives a very vivid description of the MCML Monte Carlo modeling approach. And next two references are for our previous work on Monte Carlo modeling. Um, that's it. I hope you have listened to my presentation here, and I'll be happy to have any questions from you. Thank you so much.